Here in this problem, we are after pressure at this tank A, at container A, and then the point that this problem is trying to teach is that you can ignore weight of air comparing to weight of mercury and weight of water, because we know that gamma of air is 11.9 Newton per meter cubed, while gamma of mercury, for example, is like 13300 Newton per meter cube, and we know that gamma of water is like 9790 Newton per meter cubed. So it's obvious that weight of air as a gas is much smaller than weight of mercury and weight of water. So you can just ignore the change in pressure caused by weight of air. So here's how I do it. I start from point A and I write down pressure at point A. Then obviously we have to go down until we get to this interface here. So we can write down, because we're going down, pressure increases, we can write down plus gamma of air and then edge of air. We can do that. There's no problem with it. And obviously the final answer is going to be just a little bit more accurate, but I'm just going to ignore this term because gamma of air is very small comparing to gamma of mercury and gamma of water. So I don't write down anything although I'm going down, because I'm going down in air and air is very light. So we get to this point, which is an interface, and then obviously we can, because we are at this interface, we can jump across to here. And again, we don't need to write down anything because pressure at this point is equal to pressure at the other point, because both of these points are in the same fluid, which is mercury, and at the same level. Then at this point, I start going up and I stop at the interface here. Because I'm going up, pressure decreases, so I'm going to change this to negative sign. It decreases by gamma of mercury, because we are going up in mercury, multiplied by h of mercury, which is obviously the displacement in z direction is 32 centimeters minus this 15, and we have to convert it to meter. So it's like 0.32 minus 0.15. And we are here, and obviously we are at the interface, so we can jump across to this point over there. And then I start going down in air, again, because I'm going down in air, and air is very light. I ignore that term, and I don't write it down here. And I get to this interface. So I jump across to this point here, and I don't need to write anything. And then from this point, I move up until I get to the free surface. So I move up until we get to this free surface, and we know what's pressure here, which is equal to atmospheric pressure, because this is open to the atmosphere. So how much we go up, and we're going up in water, and we're going up, so it's negative, it's minus gamma of water multiplied by this length here, delta z. That's the delta z, that's the displacement in z direction when we go up from this point to that point, to the free surface. This term is equal to L sine theta, this theta here, which is 55 degrees. So I can say L sine 55 degrees. So that's the total height minus this 18 that we have here. And I convert it to meter. This equals to PA, or atmospheric pressure, which is 1 atmosphere. So this equals to P atmosphere. Remember, we are after this PA, so I say PA equals to atmospheric pressure, 1 atmosphere, which is equal to 101,350 Pascal. This is this term here, atmospheric pressure, and these two terms will be transferred to the right side, so this negative sign will be converted to positive, plus gamma of mercury, which is 13300, times h of mercury, which is 0.17, This goes to the other side, so it becomes positive, plus gamma of water, which is 9790, multiplied by this displacement in z direction, L sine 55. The value of L is given 1.2, so it's multiplied by 1.2 sine 55 minus 0.18, and then that's it. And if you simplify this, you get the value of pressure at A, which is 100, approximately pressure at point A is approximately 131,840 Pascal. Or you can say approximately 131.8 kilo Pascal.